Buenas tardes a todas, a todos. Qué bueno verlos en este cierre de la Semana del Biodiseño de la Industria. Ha sido intenso, muchas actividades, unas conversaciones diversas en torno a este tema que conecta al diseño con la ingeniería a partir del desarrollo y manufactura de nuevos materiales biológicos. Eh, Hemos estado con una visita muy interesante de la Universidad de California, Davis, pero también estuvimos escuchando charlas del California College of the Arts y del Biodesign Challenge hace algunos días. La semana ha tenido foco en diversos tópicos y hoy vamos a centrarnos siempre en el marco del biodiseño, de la industria de la manufactura. Vamos a centrarnos en el ángulo más científico y cómo se conecta el diseño y las ciencias en el contexto de esta conversación. Y para eso tenemos un programa donde vamos a escuchar dos charlas con rondas de preguntas y respuestas intercaladas entre sí. Les recuerdo que esto está siendo transmitido por Zoom o ETV con traducción simultánea, en el caso que elijan ese atributo en la plataforma. Eh, y contarles brevemente quiénes van a ser nuestras charlistas. Eh, Voy a leer literal los títulos, que siempre es importante. Tenemos por un lado a Javiera Norambuena, de la Universidad del Desarrollo, PhD en Microbial Biology, del Rogers School of Environmental and Biological Sciences, investigadora asociada de la UPLA. Y por otro lado, vamos a tener a Alejandra Ruiz de la Universidad de California, Davis. Alejandra es Master in Fine Arts and Design de esa universidad. Obtuvo el Savageaux Award de este año en estas materias y muy vinculado a la investigación del micelio y es Bachelor of Science en Engineering. Además, aprovechar de contarles que el día de ayer se produjo una sesión, la primera del Future Fungi Award, una instancia que reúne y es patrocinada por inversionistas de la Unión Europea, donde se discuten y seleccionan diversos papers y contenidos en torno al mundo fungi o fungi. Y en ese sentido, hubo en el Futures Fungi Award de ayer cerca de 260 postulaciones y una investigación de la misma Alejandra Ruiz que va a estar presentando hoy y colaboradoras en esa materia como Cristina Cogdel y Valeria La Sabonara, que nos acompañaron hace algunos días, fueron seleccionadas finalistas en esa distinguida y selectiva competición. Entonces, de cierto modo, tenemos una élite en este momento de personas acá hablando. It happens to be, claro. Ocurre que justo ocurre esto ayer y tenemos la suerte de estar acá en la Universidad del Desarrollo con esta élite de personas que saben y trabajan en torno al micelio mucha fuerza. Así que voy a dejar ahora felicitaciones, Alejandra, por eso y vamos a escucharte ya expandir en esta idea en unos minutos más. Voy a dejar a Javiera Buena para que parta, a lo cual se va a suceder, como les contaba, en preguntas y luego Alejandra con su charla. Que estén bien.
Hola, buenas tardes a todas y todos. Yo les voy a hablar de algo un poco distinto a lo que han visto, quizás, no tanto porque hay micelio incluido, pero no mucho, porque sé que las expertas son otras. Así que yo les voy a hablar de mi área. Soy microbióloga y trabajo aquí con la doctora Natalie en la Facultad de Ingeniería, de Ingeniería, no, de diseño, de diseño. Perdón, y ahí está, diseño, perdón, perdón. Y trabajamos en una idea para remediar sustentablemente las aguas de desechos de la salmonicultura. Así que les voy a hablar un poquito de esto. Antes de, las chicas que estuvieron en la clase que yo estuve con ustedes ya vieron parte de, así que perdón si se repite, pero hay partes un poco repetidas. Ya, ¿qué son los materiales biofabricados? Usualmente son a partir de organismos, materias biológicas. Esa es la idea de un material biofabricado. Y son productos, subproductos o cosas modificadas genéticamente que nosotros hacemos para producir lo que nos interesa. En este caso nos interesan los materiales. Uy. Ah, ya. Ya. ¿Qué organismos pueden hacer esto? Entre ellos, esto no apunta, ¿cierto? Ya. Entre ellos, los hongos, las bacterias y los insectos. Las bacterias son diversas. Existen algunas que hacen fotosíntesis, existen otras que viven en ambiente extremo, en el frío, etc. A ustedes yo creo que se les olvida que el algodón viene de biología, viene de una planta. Las plantas producen algodón, ¿ya? ¿Qué más? Bueno, los micelios, que vamos a tener una charla más profunda de los micelios, pero los hongos producen micelios y las arañas. Ustedes sabían de las arañas, ¿cierto? ¿Sí? Ya. ¿Qué más? Para poder producir este material biofabricado necesitamos comida. Como son seres biológicos, están vivos y necesitan comer. ¿Qué pueden comer? Materiales. Entre esos materiales, por ejemplo, los hongos pueden comer árboles. Las bacterias pueden comer distintos sustratos que hay en el suelo o contaminantes. Las que hacen fotosíntesis pueden comer luz o utilizar luz para crecer. Y, por ejemplo, en el caso de los insectos, a veces pueden comer otros insectos. ¿Ya? ¿Qué más podemos tener en este material biofabricado? ¿Un molde o una superficie en el que crezcan? ¿Para qué? Para moldear lo que a ustedes les interese como diseñadores obtener o para que el material tenga alguna forma específica. Ya, vamos a hablar un poquito de los tipos de organismos que son capaces de producir biomateriales. Igual tengo harto de micelio en la presentación, perdón. Pero es cortito, es cortito. Sí, es que el mejor biomaterial o el más estudiado después del algodón, entonces, ya. Los hongos. Los hongos son organismos vivos que utilizan, hoy no se ve, como comida, material de desecho. Ellos son los principales degradadores en el ambiente. ¿Ya? Cuando uno tiene un material en descomposición, ¿quiénes son los que crecen y ayudan a degradar? Los hongos con bacterias. Entonces, sin los hongos no podemos reciclar materia muerta. Entre las cosas que podemos reciclar son desechos agroindustriales o otra cosa que a ustedes les interese volver a ser biológicamente no contaminante. Dejémoslo en esa definición. Ya, ¿y qué obtenemos del hongo? Lo que nos van a hablar más tarde, que es el micelio. ¿Cómo se podría ver el micelio si ustedes producen grandes cantidades, como lo que se ve en la orillita? Ya, ¿cuál es el ciclo a grandes rasgos? Los hongos tienen también depende del hongo. Esto es otra cosa importante. Los hongos que ustedes ven en el campo, ese típico honguito de pitufo que sale en el campo, es un tipo de hongo. Existen otros hongos que se llaman levaduras, que no forman este tipo de estructuras. Los aspergillus y los penicillium, que son los que crecen en el pan, ustedes han visto el pan que se le honguea, ese otro tipo de hongo. ¿Ya? Algunos de ellos producen micelio. Los hongos esporulan, este micelio son básicamente ramitas. Veámoslos como las raíces de algo. ¿Ya? Es un estilo raíz. Después esto crece y se forman los cuerpos fructíferos. Y estos cuerpos fructíferos al empezar a crecer liberan de nuevo las esporas. Y este es un ciclo básico de reproducción de los hongos. ¿Por qué ustedes los ven en el bosque? Porque degradan madera o celulosa. Lo principal que ocupan para comer es celulosa. Ya. ¿Qué es lo que podemos hacer con esto? Y este es el material súper estudiado y el como gold standard de un biomaterial. Es porque es fácil de moldear. Y ustedes le pueden dar la forma y el tipo de diseño que ustedes quieran. Existe una página que no sé si las chicas, bueno, yo creo que la conocen, que se llama Mou Home. Y básicamente lo que venden son distintos tipos de materiales hechos a través de micelio. Aquí hay distintos tipos de micelio porque les dan distinta comida y de acuerdo a la comida que tengan, se ven distintos colores. ¿Ya? ¿Cuál es la gracia de esto? Que ustedes pueden moldear dónde crece el hongo. Y ahora vamos a ver cómo se crecen los hongos, para que tengan una idea de cómo se vería esto en la vida real. ¿Mm? Era con sonido. ¿Tiene sonido o no? ¿Te reproduce? No está reproduciendo. Ya, bueno, no importa. Sirve para relajarse el video. Ahí están los hongos creciendo en un laboratorio. Ese es el producto final. Ya que no tiene sonido, yo les voy contando como es lo que más o menos dicen. Porque no me acuerdo exactamente lo que dice. Y ahí se vería como el entremedio de su material y ahí hay un producto final, por ejemplo. Eso es lo que pasa en tiempo real cuando empieza a crecer tu hongo, es un bioreactor. Básicamente uno les da comida constantemente y los hongos crecen a un rango constante. Ahí está donde se crecen en un shaker, la comida que le dan, y después está el material. Y se van almacenando para después producir lo que quieran producirse. El otro no va a tener tampoco. No. Y ahí, por ejemplo, hay un molde. En este caso, esta empresa se dedica a hacer paneles de distintas cosas. Unas son para sonido, otros son pisos y diseño en general, que vamos a verlo en la diapo que sigue. Sonido igual a par. Entonces, ¿qué es lo que se hace? No sé si vieron que habían unos frasquitos más chicos que otros y un shaker grande. Se hace un cultivo primario. El cultivo primario es que creas una cantidad de masa suficiente para transferirla a un shaker más grande. Entonces, cuando ya tienes el producto más grande, se puede obtener el micelio. Oh, oh. Ya, la que sigue. Entonces, ¿qué es lo que hacen en esta compañía? Pisos, ecocuero y lo más interesante que es los paneles que ustedes vieron, casi todas las formas que se mostraban en el video eran paneles, y estos paneles los colorean. Entonces se puede hacer una mezcla entre la ciencia y el diseño bien, bien interesante aquí. ¿Ya? ¿Qué más? Aquí están las formas. Cada forma tiene distintas propiedades de absorción de sonido. Entonces, dependiendo de lo que ustedes quieran en un cuarto o qué tipo de ambiente van a tener para hacer, por ejemplo, una charla, se ocupan distintos de estos paneles. Cada uno tiene propiedades auditivas distintas, absorbe distintas frecuencias y distintas cantidades. Entonces, dependiendo de la forma, el mismo material puede darle distintas propiedades a una misma habitación. Ya, insectos. ¿Qué les suena a ustedes? Probablemente el gusano de la seda, el más conocido. ¿Qué otro insecto se puede ocupar? Y que ahora se está ocupando bastante, son las arañas. ¿Qué comen las arañas? Otros insectos. ¿Qué producen? Las redes de arañas, las telarañas o las sedas. ¿Qué es lo que se hace ahora? ¿O qué es por qué se intentan ocupar las arañas? Usted, no sé si se sabe que dependiendo del tipo de telaraña que hagan las arañas, tienen distintas propiedades físicas y pueden absorber distintas cosas. Estas arañas pueden formar telarañas como tal y los agregados, ya estas formas como cilíndricas. Estas dos cosas tienen propiedades físicas diferentes. Entonces esas propiedades físicas diferentes se pueden ocupar para diferentes materiales. ¿Por qué no se ha ocupado tanto las arañas? Porque crecen más lento que los gusanos. Los gusanos son súper fáciles de tener y por eso el gusano de la seda es el más conocido. Aquí está lo que se hace después de obtener una telaraña. Estas telarañas se pueden tratar químicamente y obtener distintos materiales biofabricados. ¿Qué sería? películas, hidrogeles, incluso se pueden obtener esponjas, fibras de nanoscala y textiles. Usted obtiene la seda de la araña, hacen un tratamiento químico posterior y obtienen diferentes materiales. Actualmente, ¿para qué se está usando la telaraña? Digámoslo burdamente, para huesos. Se están modificando genéticamente estas fibras para poder producir huesos. Entonces, ¿cómo se hace? Se le pone una cosa que se llama un vector adentro de una araña, y esto ¿qué produce? Distintas fibras. Y estas fibras tienen características distintas que permiten o pueden simular un hueso. En esto se está trabajando ahora en las telarañas. ¿Qué más? Las algas. Las algas, en este caso, en la que les voy a hablar, se llama Chlamydomonas reniardi. ¿Qué hacen las algas? Comen, comillas, comen luz. Utilizan la luz para crecer. ¿Qué es lo que se está haciendo ahora? Se están haciendo capas con algas. Entonces hace un biomaterial en el que la capa puede tener algas y absorber luz. ¿Cómo ocupan la luz? El CO2 se fija dentro de la alga y se produce oxígeno. O sea, estamos disminuyendo también los gases de efecto invernadero, que uno de ellos es el CO2. Aquí viene el video, sí. Que este sí debería tener sonido, pero no va a tener sonido. No, ese. Ese. No se puede poner sonido, ¿cierto?
Puede que se resuelvan unos minutos más. Si de repente...
Ya podemos volver. Sí, pues sigo y después volvemos a esa. Ya. Ya, si se puede resolver, vuelvo a esa. Si no, está entretenido el video. Es que no me acuerdo todo lo que dicen, entonces no les puedo ir contando. Sí. Es que no me lo sé. Sí, sigamos en la presentación nomás. Ya. Me falta. No sé. En el computador. Sí. Dale. Sí. No, pero sigamos con la presentación. Ya. Espérate, para atrás. Dale para atrás. Porque esto no funciona. Dale, sí. Ya. Para atrás. Ahora les voy a hablar de las bacterias, que son mi microorganismo favorito. Son organismos vivos y viven en todos nosotros. Si me pasáis la diapo, no funciona. Ya, ¿qué ocupan para comer las bacterias? Medio. Nosotros en el laboratorio le damos medio, en el ambiente, ¿qué comen? Glucosa, desechos, un montón de cosas. ¿En qué las podemos poner? En un molde, en una superficie también. Entonces, ¿qué empresa tiene aplicadas las bacterias para utilizar o crear biomateriales? Es Modern Synthesis, que es la que la profe Nati, para los que son de la clase, les pasó las zapatillas que están hechas de micelio, en la misma empresa. Y ellos ahora están creando fibras textiles hechas a través de la fermentación de bacterias. ¿Qué es lo que hacen? Este material se usa creciendo las bacterias sobre nanocelulosa y produce un material súper liviano y es un tipo de fábrica nuevo. Estas fibras de nanocelulosa son pequeñitas y tienen 8 veces, son más resistentes que otros materiales. Entonces, Ah, no, aquí había un video, ya no está. Ya. Entonces aquí estas telas se producen con bacterias. ¿Qué es lo que hacemos nosotros? Nosotros ocupamos bacterias, en este caso Morganella morgani, y ¿cómo se ven las bacterias? Esta es una microscopía electrónica de una bacteria, que es la que ustedes a veces pueden haber visto en algún lado. Esta bacteria tiene la capacidad de generar extracelularmente, o sea, en su medio, nanopartículas. ¿Qué es una nanopartícula? Son partículas de tamaño nanométrico, estos puntos que ustedes ven aquí. ¿Cuál es la gracia de este organismo? Que lo hace a temperaturas bajas y puede hacer nanopartículas esenciales. ¿Por qué? La mayoría de las bacterias que se conocen hacen nanopartículas de óxidos, que cambian las propiedades químicas y físicas que tienen esas nanopartículas. ¿Mm? Ya. ¿Y por qué es importante? Buen punto. Porque después lo van a ver en las fotos de nosotros, ese hot dog que le decimos, es una bacteria. ¿Ya? Y los puntitos que van a ver al lado en las fotos que siguen son nanopartículas. Ya. Entonces, ¿qué le damos nosotros a las bacterias? Le damos un medio y metales. Entonces, ¿qué es lo que pasa? En un modelo de tipo esquema tenemos un elemento elemental, en este caso es azul porque el cobre 2 es azul y el cobre 0, que sería la nanopartícula, es naranjo. Entonces tenemos que la bacteria, ¿qué es lo que cataliza? Que esta partícula se convierta en una nanopartícula. ¿Cómo se ve? Esto se puede ver al ojo. Estas son las bacterias crecidas solo con medio. Estas son las bacterias crecidas solo con cobre y se ven naranjas. Y estas son las bacterias crecidas con plata y se ven de color plata. Entonces uno puede ver al ojo el color y las nanopartículas que se están produciendo. Ya. ¿Por qué nosotros queremos tratar aguas de salmones? ¿O por qué en nuestro proyecto nos interesa este tema? Nosotros somos el segundo productor de salmónidos del mundo. Producimos una gran cantidad de este pescado. ¿Cuál es el problema? Los salmones en el medio ambiente generan mucha contaminación. De hecho, los ríos del sur están llenos de antibióticos, metales, etc. Entonces, es un problema ambiental súper grave. ¿Qué es lo que se hace en Europa? Todo esto se crece indoor. Entonces, se tienen los salmones en un cultivo cerrado, cosa que el agua no vuelva a caer al ambiente y arruine el ambiente. ¿Qué es lo que se está haciendo en Chile? Están encerrando los salmones en una caja, pero que el agua del río entra y el agua del río sale. Entonces, igual se vierte el contaminante al ambiente. ¿Dónde se produce esto? Lo otro peor, la otra mala noticia en Chile es que es la parte más bonita, que es el sur. Entonces todo el sur está siendo contaminado con productos de la empresa salmonera. No es esto para que no coman salmón, pero el salmón tiene hartos problemas ambientales que no vamos a entrar en más detalle hoy, pero tiene muchos problemas medioambientales. Entonces, ¿cómo es el proceso de crecimiento de salmónido? Se hace un desove y se fertiliza. Todo esto es hasta aquí es indoor. Los smolt, dependiendo se pueden crecer cerca de los lagos y se engordan hasta cierto punto en que del agua del lago se cambia a un agua de mar. Entonces también hay otro problema ambiental, que es que se mueven patógenos y cosas que crecen en los peces desde una agua dulce a un agua salada. Entonces ya estamos moviendo más encima, más contaminantes de un tipo de agua al otro. ¿Qué es lo que pasa después? Se cosechan, se procesan y básicamente se vende el producto. ¿Qué es lo que se hace en los sistemas de cultivo indoor? Básicamente se sitúa en un sistema de agua recircularizado. Y estos peces se van cambiando sí de estanque, porque el agua dulce y el agua salada son distintas, pero se recicla el agua. La cosa es que se bote y se use la menos cantidad de agua posible. ¿Qué es lo que pasa en esto? Estas aguas de tratamiento, estos filtros que tienen, remueven materia orgánica. Los peces comen peces. Esos peces tienen metales. ¿Qué es lo que pasa o qué efecto tienen estos metales en los peces? Pueden producir embrios anormales, disminuyen el crecimiento y disminuyen la cantidad de crías, o sea, que no son crías, la cantidad de huevos que ponen. Entonces, ¿qué pasa? Todo esto afecta a la producción de los salmónidos. Y si recirculamos el agua y no le sacamos los metales, ¿qué pasa? Nos puede producir un problema en la producción industrial. Entonces, ¿cuál es nuestra idea? Que ocupemos papel. Todavía no les cuento la idea, les estoy contando los problemas. Les estoy contando los problemas todavía. Entonces tenemos una bacteria que hace nanopartículas, un medio metal, tenemos salmones. Ahora tenemos un molde. Les voy a contar por qué vamos a ocupar todo esto al final. ¿Qué molde vamos a ocupar nosotros? El papel. Chile, el productor número 9 de papel, entonces otra de las principales industrias que tenemos en el país. Por eso estamos tratando de mezclar salmones en nuestra industria 2. Bueno, la industria 1 es el cobre, que también está parte del proyecto, industria 2 salmones, industria 9 papel. Entonces, ¿en qué vamos a ocupar o vamos a hacer nuestro sistema? En papel. Ya. Antes de que les cuente también la historia, les tengo que contar otro pequeño detalle. Las bacterias tienen una capacidad súper interesante, que es el pegarse a las superficies. Esto pasa en su cepillo de dientes y por eso ustedes lo tienen que cambiar, ¿ya? No puede usar el cepillo de dientes por 5 años porque le crece esta biopelícula arriba de su cepillo de dientes. Entonces, las bacterias se pegan a superficies, empiezan a crecer y forman microcolonias. Estas microcolonias pueden crecer y pueden ser visibles al ojo humano, ¿ya? ¿Y qué pasa después? En algún momento se agotan los nutrientes y esto se libera y las bacterias se liberan y van a buscar una nueva superficie o un nuevo lugar que tenga comida. Ya van a ver por qué les expliqué todas estas cosas. Porque nosotros queremos ocupar este papel para hacer una biopelícula. Esta biopelícula de mis bacterias tendrá la capacidad de hacer nanopartículas de metales. Entonces, de esta manera, ocupamos un soporte, un microorganismo y biofabricamos nanopartículas a partir de aguas residuales del cultivo de salmónidos. ¿Para qué? Para remover metales. Entonces, ¿cuál es nuestra idea? Esto es un típico cultivo RAS, que son los de recirculación de aguas. En este tanque, cuando se saca el agua para volver a entrarla, se desinfecta. Existe un filtro biológico también, que saca los compuestos orgánicos. Y nosotros proponemos poner otro filtro que remueva los metales. De esta manera tenemos un agua sin carbono alto, sin metales y desinfectada que puede volver a los salmones. Esa es nuestra idea. Ya, es la idea que les acabo de contar. Nos tenemos el video, ¿cierto? Sí sería bueno que tuviera el sonido. ¿Cómo vemos nosotros la nanopartícula? ¿Cómo se ve cómo obtenemos esa foto que yo les mostré antes de los puntitos?
Scientists and engineers design transistors that are around the width of a strand of DNA? How do we even take pictures of such nanoparticle transistors? Well, that's the role of the electron microscope, which is literally changed the way humanity sees the micro and nanoscopic world. Due to the Have you ever wondered how scientists and engineers found the width of a strand of DNA? How do we even take pictures of such nanoscopic transistors? Well, that's the role of the electron microscope, which has literally changed the way humanity sees the micro and nanoscopic world. Don't believe us? Take this European peacock butterfly, for example. When we zoom in on its wing using a light microscope, we see that it's composed of tiny overlapping scales. But when we zoom in using an electron microscope, we can clearly see the shape of each scale. And zooming in further, we see how the scales have a truly incredible texture entirely foreign to atoms. And with today's technology, this microscope can zoom in millions of times to where it's able to capture images of individual atoms. There are two main types of electron microscopes. The scanning electron microscope, or SEM, is used to see surface images like this butterfly wing.
Ya, entonces ese microscopio, el que está ahí, esto es un cepillo de dientes, de hecho. Así que si no lo han cambiado, vayan a su casa, bótenlo y compren uno nuevo, por favor, porque esto está creciendo en su cepillo de dientes. Ya, estos son bacterias. Y con eso es suficiente. Y esto es lo que o lo que hicimos nosotros en nuestro proyecto, ver cómo estas bacterias se pegan en un papel y pueden formar biopelículas y nanopartículas. Entonces, ¿cómo lo vemos? Todo lo que brilla es una nanopartícula. ¿Por qué? Porque llega un electrón y las partículas que son metálicas lo reflejan y se devuelve y brilla. Todo lo que está oscuro es papel o bacteria. ¿Ya? Entonces, ¿qué fue lo que hicimos nosotras? Primero experimentamos con los días de esta biopelícula. Si las dejamos crecer un día, si las dejamos crecer 2 días, si las dejamos crecer 3 días. Sacamos el papel y lo llevamos a un SEM, que es el que yo les mostré antes. Esto es esto va a ser nuestro paper, que se ven tan bonitas. Esto es día 1, si ustedes se fijan, hay menos bacterias que el día 2 y que el día 3. En el día 3 ya hay una cueva de bacterias, básicamente. Los puntitos, no sé si de atrás se ven los puntitos, esos puntitos son nanopartículas. Por alguna razón, en el día 1 ellas forman más puntitos que el resto de los días, y se puede ver. ¿Qué pasa si lo cuantificamos? O sea, ¿qué pasa solo en el papel? Si nos vemos las células, se ve claramente que en el día 1 se producen muchas más nanopartículas que en el día 2. ¿Y qué es lo otro interesante? Todavía no se sabe cómo las producen. Es desconocido hasta la fecha cómo estas bacterias producen estas nanopartículas. Pero creo que nosotros tenemos la foto que resuelve esa disyuntiva. No sé si se fijan aquí, que se ve como una telita con cosas brillantes encima, y aquí se ve como que la telita se rompió. Como que la bacteria engloba el tóxico, porque la plata es un tóxico para ellos, y en un momento es demasiado y rompe la telita y se liberan aglomerados de nanopartículas. En los días posteriores, en el día 2 no encontramos, esta es como la más parecida, pero si se fijan tienen puntitos de nanopartículas creciendo arriba de ella. Aquí tenemos una bacteria mutante de nanopartículas. Se ve como que tuviera tumores nanoparticulosos, pero son nanopartículas de plata. Con el SEM podemos medir también qué hay en cada puntito. Y si uno hace un análisis de qué elemento tienen plata. Así que podemos confirmar que es plata. ¿Qué es lo que yo hice? ¿Qué es lo que hago acá también con los chicos que están aquí en la presentación? Ocupo el XRF. ¿Qué es lo que básicamente nos entrega? Nos entrega la composición elemental de nuestra muestra. Entonces yo llevo el papel, voy al XRF y veo qué metales tengo en este papel. Y los puedo cuantificar. Cuando los cuantifico, en el día 1 tenemos 537 pongámosle concentración, no les voy a decir el número específico, pero ya, concentración, día 2 es similar y el día 3 ya baja. Si analizamos o juntamos ambos datos, vemos que en el día 1 sí hay más nanopartículas en el papel que en el día 2, pero por alguna razón en el día 2 igual acumula una cantidad significativa de plata, pero puede que no sea en forma de nanopartículas. Entonces nosotros decidimos para el resto de los experimentos utilizar el día 1. ¿Qué hicimos después? No tengo las fotos de esto porque las sacamos hoy día, así que no están. La iba a poner, pero no alcanzaron a llegar. Ahora escogimos día 1 y ¿qué hicimos? Distintas concentraciones de plata para ver si afectaba, cuánta plata le ponemos, cuántas nanopartículas. Y aquí ven un ejemplo de lo que obtuvimos de distintas concentraciones de plata. Concentraciones de plata baja, concentraciones de plata alta. Si ustedes se fijan, hay una tendencia a incrementar hasta que después baja de nuevo. La que produce más nanopartículas es cuando nosotros agregamos esta concentración de plata. Y me da lata no tener la imagen porque de verdad se ve todo cubierto con nanopartículas de plata el papel. Y la gracia de estos papeles es que ustedes lo pueden ver al ojo. Tienen una propiedad organoléptica. Este es tu papel solo con células, este es con 5 milimolar de plata y este es con 15. Y ustedes claramente ven que hay un incremento en la color plomo del papel. Y esta es la que tiene más concentración en el XRF. Entonces, nuestra propuesta, que hasta ahora anda, vamos que morganela, a través de medio y metales, es capaz de pegarse un papel y producir nanopartículas. Y eso. Tengo los papeles si alguien los quiere tocar y ver. No los huelan. No los huelan. Todo el mundo me reclama que huelen mal. ¿Tienen preguntas a alguien?
Hola.
A lot of questions.
So I have a quick question about the biofilm paper. Why not change the geometry of it to see if that alters the concentration?
The next step is we're going to change different, what is thickness of the paper? Thickness of the paper. So we're going to try a lighter paper and a thicker paper than the one that we're using to see if it affects the amount of nanoparticles that stick to the paper or not. So that's, yeah, it's a great idea because we're doing it.
Hola, muy interesante la presentación. Mi duda es, ¿qué tan fácil es la escalabilidad para que sea una solución, pues, en toda la industria?
Esa es una excelente pregunta y ese es el problema de los biomateriales y de las cosas biofabricadas, que de escalar son bien difíciles. Entonces, tenemos otra idea de cómo se podría mejorar, quizás hacer un liofilizado o alguna cosa más que dure más, porque ¿cuál es el problema? Lo que yo estoy haciendo es papel que está vivo. Entonces, ese ya es un problema para la industria, porque ¿cómo vaya a mantener vivo? Entonces, eso sí, tiene un problema de escalamiento. Ese es nuestro mayor problema.
Hola. Bueno, súper interesante la presentación, muchas gracias. Ya, yo tengo dos preguntas. Una, no me quedó claro de dónde vienen. Entiendo que hay metales pesados, pero vienen de los peces, de los antibióticos, no sé de dónde. Y la otra pregunta es, ¿qué tienen pensado un poco con estas nanopartículas obtenidas? O sea, hacer papel con nanopartículas.
Ya, la primera pregunta es una pregunta compleja que implica ecotoxicología, pero en respuesta simple es una biomagnificación de contaminantes. El mercurio, no sé si ustedes saben que el metilmercurio causó una enfermedad en Japón que tuvo varios niños que tenían deformidad y problemas neurológicos. Ya, eso se debe a una bioacumulación de mercurio a través de la cadena trófica. ¿Y qué significa? Que tú tienes un zooplancton que come bacterias en el agua. Esas bacterias tienen metilmercurio. El zooplancton, digamos que absorbe 20. Al zooplancton se lo come, vamos a saltarnos varias partes y llega un pez chico. Ese pez chico, en vez de tener 20, bioacumula 40. El pez grande bioacumula 100. Entonces, cuando uno se lo come, uno que come más de un pescado al día, o etcétera, tenéis 500. Es parte de la contaminación humana hacia la... Bueno, el mercurio, es que el mercurio es complejo, porque viene de también fuentes naturales, como los volcanes. Y en Chile tenemos harta actividad volcánica, entonces como echémosle 50-50 en Chile. En el resto del mundo que no hay volcanes, no sé. Pero existe eso, sobre todo con el metilmercurio, que es por el que recomiendan no comer mucho pescado, y el cobre también tiene el mismo efecto. Entonces por eso y los pescados comen pescado. El pellet de pescado es pez liofilizado. Entonces eso ya tiene una alta cantidad de metales. Ya, la segunda pregunta era... De hecho, yo creo que nuestra idea es ver las propiedades antimicrobianas del papel, porque escalarlo como para algo más fácil sería hacer un bioreactor, más que un papel. Así que...
So I think she asked something of the same questions I had. I was looking at the number of different elements that are in the water plus the antibiotics. So you think that one single paper with the nanoparticles is going to be able to basically block all of these from the downstream? Or that's the hope? Ambitious.
I love your positivity because that will be awesome. That will be great. But this organism has the ability to basically it's kind of like a cool little guy because we add 15 millimolars of silver in the environment, we have parts per million. So it's able to like in a mining drainage, you have like 5 millimolar maximum copper, 10 maybe. So it will be able to like make it all nanoparticles. But the problem is like, how do we keep it alive so you can make it over time? So that's why a bioreactor might be better suited for it. But hopefully, yes, it solves all the contamination problems.
Gracias por tu presentación, Natalia. Tú mostraste más o menos cómo es como el estanque de cultivo del salmón. Yo pensaba como dónde iría el papel, pues como dónde ves que podría ir la aplicación como el papel, si el papel es como por ahora algo temporal en el que se encontró que captura, pues que pueden como inocular las bacterias y luego generar la captura, y cómo sería la resistencia de ese medio del papel ante la exposición al agua como permanentemente.
Muy buena pregunta. Queremos ponerlo como un filtro de papel. Básicamente sería como una maquinita, un tratamiento externo que tiene distintas membranas con el papel. El problema, lo que comentaba con él, es que no sé cuánto me durará ese biofiltro. ¿Por qué? Porque las bacterias van a durar cierta cantidad de días. Esa es la gracia de los sistemas que ocupan en la acuicultura actualmente, que las bacterias se alimentan de lo que tú les vas poniendo. Estas bacterias no se alimentan del metal. Solo se defienden del metal haciendo nanopartículas. Entonces, quizás el que se agregue todo esto antes del filtro biológico les daría nutrientes, porque el desecho del agua de salmón tiene una gran cantidad de materia orgánica. Entonces, eso puede que nos favorezca la producción de nano. Pero hay que evaluar todavía, y tengo idea de otro material que no voy a decir. Secreto de Estado.
¿Hay más preguntas? ¿Hay preguntas en el chat? No. Okay, so Javiera, thank you very much. It's sí. So, one more question. What is it that smells foul? The bacteria or the... Ah, okay.
This was isolated from, so this bacteria was isolated from fish. So canned fish, like the canned tuna, I don't remember exactly which fish, but it was found in the fish skin, like little, like whatever we eat, it was on top of it. So that's why we think it evolved to have this ability to make nanoparticles externally, because it's exposed to like the metal that you put the fish in the can. So that's where. No, así que otras bacterias no tenían eso. Me quedo al lado tuyo.
Así quería preguntarte, esta bacteria, ¿cómo se relaciona con los humanos? Pues
no es patógeno humano. Esa es la gracia. Es patógeno de peces. Por ende, también sería otro problema si es que lo ocupamos vivo en sí en un sistema acuático, porque ¿qué pasa si se te arranca? Entonces, sí.
Okay, no further questions then? Okay, thanks, Javiera. Very interesting presentation. Now, yes. So I think what at least I make the most out of this is that there are very different disciplines and each discipline has its own abilities. So this is all very complex stuff and people from other fields of knowledge might have some trouble understanding and even more trouble trying to experiment. So I think it's very interesting that we have this collaboration because modern problems require interdisciplinary solutions, and having teams integrated by multiple disciplines always take the problem solving one step further. And so we're going to wait for a few minutes until 3 o'clock for Alejandra Ruiz's talk, and 5 more minutes. Great. I could tell jokes in the meantime. No, I can't. a real pleasure to have the people from California Davis in here. We have been learning a lot during this week, I think especially our students, and ultimately everything we do here is about sending better professionals into the world. And we are convinced that international experience, interdisciplinary experience, and experience with hands-on experiments and technology offers them a better way of learning things to go into the world. So without further ado, Alejandra Ruiz, everyone.
Hola, hello. Thank you so much for being here, you all, and as well as the people that is like on the Zoom. Working? Yes. Okay. So I am Alejandra Ruiz. I am from Colombia. My background actually is in fashion design. I studied fashion design some years ago. But while I was studying fashion design, I found out a super interesting topic and actually a very concerning issue. So I found out that in my education, there was like barely something about what happened to the garments or textiles that I was creating after their end of life, right? Not even in the end of life, like after people purchased them, there was like no information. Like as designers, after selling our things, we received like very good training until selling the things we created, but afterwards, like, so where are the clothes, right? Where are the textiles? What happens during their use? What are the meanings people are creating around them? Also how they dispose them and what happens with that. So that took me to understand that actually there's a super, super complicated issue on textile waste. So if you're Chilean, you might know about this, right? Because Chile is one of the most affected countries by the exports of secondhand clothes. So just like for statistics that are like really of concern, so more than 100 billion garments are being produced globally per year, this especially after 2015. 100 billion garments. Think about how many you have in your closet, right? Imagine like 100 billion garments per year, right? Near 60% of the fibers used for clothes are synthetic fibers. Around 2/3 of the textiles at their end of life cycle, they go to the landfills. And only 15% of those are diverted from the environment and from landfills. That means only 15% are recycled. So imagine the importance of this issue, right? And just to understand how it happens, if you have a look on the tags that you have in your clothes on the sides, you're going to see the composition. And this is really why this is a material problem, because we are mixing a bunch of organic as well as petrochemical and synthetic, like artificial fibers to create our clothes, which really difficults the process of sorting and recycling these garments. So these are some of the types of textile waste that you can find along the production and consumption of textiles and clothing, especially. So like scraps, leftovers of the cuts, which are like about 15 to 20% of the total amount of fabric that is used for making clothes. Then you also have inventories that are unsold. And I guess a lot of you might have heard about all the stories about destroying inventories because some brands are not able to sell them. And also clothes bales, right? If you go to Bandera here in Santiago, you're going to see a lot of these market. So this is like a big issue, right? During the talks that we have had like here in the Chilean Biodesign and Industry Week, I really kind of thought that we are like recently awakening the understanding that these linear models are like no longer sustainable. And that's like, for me, it's similar to like when we discovered that the earth was not flat, right? We're like discovering that like take, use, like, and discard is like no longer, it doesn't benefit anybody, the environment, us humans, right? And we're starting to think a little bit more circular. Although this looks pretty circular, but still not quite there. So it's still pretty linear because the materials that we are using are actually, it's not possible to recycle them or turn them into something else in the scale that we need it to happen, right? So just 15% of them are like actually transformed or recycled, reused. So what do we do with this? This is like a really difficult issue. So I like thought about this and then said like, okay, well, I think there are like basically two approaches. We can prevent or we can remediate what is already created, right? And here's like so interesting to think that how these are also approaches from biodesign, right? We have a lot of biodesigners working on developing new materials that can replace synthetic and fossil-based materials, which is great, right? But there are also all the tons of mixed fiber textile waste, especially, that what can we do with that? We have to remediate them, right? We have to try to take them away from the environment. So my project focuses on diverting by reusing through materials design. So my proposal is create materials using textile waste. So how do people imagine that the materials of the future should be, right? So some answers that I propose, or how for me this makes sense, I would think of materials that have circular lifetimes, right? They're not linear, they kind of circulate in between like life cycles. Local, they're locally sourced, and like we saw in a couple of presentations how a local component is so important for reducing carbon footprint. Ethically sourced, right? Who are we taking the things from? The soil, the indigenous community, right? Energy conscious, like how much energy are we putting into the materials we're creating? Non-toxic, right? And not only for us human beings, non-toxic for other ecosystems. And accessible, right? Do we want them to stay like in small niche, or do we want them to be more like massive? Non-extractive, right? And hopefully regenerative. Can we make materials that can help us like restore some of the ecosystems that we want to bring back from this destruction? So I picked these two words, like ethical, like kind of like associated with sustainable, and from waste. Why from waste? Because waste is super abundant, right? We are starting to see waste everywhere. And I firmly believe that waste is going to be the materials of the future. So when you have like a waste stream, right, and you want to turn it into a material, then you also face a couple of issues, right? How can I make something that was taught in a linear way? How can I make it circular? How can I make it circulated if this is like a anthropogenic waste stream that has like a lot of contaminants or like things that are like hard to work with, right? It's not even organic, like it doesn't come from any organic source. It comes from like an anthropogenic source. So this is what I call, or what I made during my design process, to mix the materials from waste with the biodesign matrix. So I started thinking, okay, what type of fiber do I have in the waste that I have? Is it a natural fiber? Is it like a synthetic fiber, or is it like mixed fibers? I want to work with mixed fibers because they are the hardest one to really transform. What type of binding method do I want to use, right? Is it just thermal, applying heat and then turning into a composite, like into a material? Or is it adding like another extra binder, or a mechanical, like conforming like of a material? So my interest was more towards composite materials. And then I asked also, okay, what type of binder? So this led me to a really interesting explorations on binders, as the binders kind of allow the composite materials to like keep circulating in like industrial economy. So you can also think like, what type of system do I want? Do I want like a closed loop recycling? Do I want like a sort of open loop recycling? Do I want my material to be biodegradable? Do I want it to be low impact? So those are like some questions that you can ask yourself as a designer when you are like starting to think about a product, in this case, a material. And those decisions definitely are going to like influence the waste that is generated, or diverted or recovered. So this led us to the first question in our research, which was explore binders that can turn textile waste into circular materials for interior design and architecture. So this, first of all, I wanted to give this research like a local component. So I created like this like kind of research tool to map the waste and understand the different forms it can take in a specific region, right? The textile waste that you're going to find here in Chile is very different from the textile waste that you're going to find in a country that manufactures clothes like Colombia, or in a country that imports clothes but consumes a lot of carpet like the USA, specifically California, where I conducted this study. So these are some of the typologies of textile waste that I found. Clothes, an already recycled shori pad, polyester bating used for mattresses, and clothes lint, which is a byproduct of laundering, right? The dryer. So I decided to work with fashion waste. So a process of transforming the raw material was like necessary. That means like transforming like from a fabric to like a particle, or like a smaller particle. And this is super interesting because this is how you explore also like the aesthetical and physical qualities of the material, of your raw ingredients, that can also at some point show up in the materials you are designing. So in that research, I started understanding and learning about biobinders. That means biopolymers used to agglomerate, bind together these fibers. So initially, I just wanted to feel how did this like biopolymers felt. So I just like explored their like, how to say, like pure expression, or like preparing them as films. But then I started mixing them with textile fibers of different types and creating like these samples. And with this, I was able also to propose or create or add like a section of like materials from waste to the ecomaterials library in our university. So excited to see how you guys are starting to make your own biomaterials or ecomaterials library here in the UDD. So these allow me to observe like a wide range of possible materials. And at that moment, like I was aiming to create like applications like at a larger scale. Larger scale, I mean things that could be produced like industrially, and ideally for interior architecture or some architectural forms. So I used like a very nice material design framework called material-driven design, where you start like approaching the material, feeling the material, understanding what are the like intrinsic properties of the material, what is it showing to you, and then what does it want to be, right? So what does the material want to be? So I'm just going to show some iterations of this process. So these were like some tiles. This is all using starch-based binders, in this case like cornstarch. So this is like creation of like a tile system that could have like some acoustical properties or insulation properties. This was another iteration of like also see how there are some combinations of different like manufacturing methods. Here I try to create like hollow shape. So I did like this exercise where I created this sculpture. Then turns out you can recover those fibers because this is a water solvent. It's a binder that is water soluble, right? So recovering the fibers from these or this, I could create these like sheets that could actually be laser cut and have like some degree of hardness. So you can actually use this for mocking up or prototyping, right? And then when I discovered that this could be laser cut, I was like, okay, I want to explore 3-dimensional shapes, but through creating sheets where I can laser cut specific forms and then turn them into 3-dimensional shapes. Finally, I was also learning about auxetic structures, and I decided to put these auxetic structures to curve apparently flat sheets of these textile composites. So these are some of the possibilities that you can also explore aesthetically, as this binder allows you to see the aesthetical properties of the textiles, right? So this is what we are doing in this case, which is like introducing a waste stream into a looping system where fibers can still be recovered and transformed into something else, thanks to the water-soluble binder, right? This is not perfect, right? We still have some issues. For example, we need to research more on coatings, on surface coatings, because the material is still not very resistant to water. And so we need to still understand a lot of like how to improve the material properties, but this was like a start. But then I was thinking like, well, you put these fibers here, they are like of mixed nature. So what happens with these materials that I'm creating, right? They cannot be endlessly in these loops, right? At some point, let's say somebody just want to discard it, or like the material might be degraded at some point that you cannot like use it, right? So what can we do with this? So then, while I was exploring the bio binders, I came to find or to meet the amazing fungi and their properties, right? So as Natalia explained us, and thank you, Natalia, for making the introduction to like mycelium materials and composites, fungi have amazing properties for biofabricating and also bioremediating, right? As Natalia was saying, mycelium, the root. Oh, I'm so sorry, I'm confusing. As Javier was saying, the root of fungi grow and agglomerate or bind material like particles that are disgregate, right? These are composites. That means you add like particles of sawdust or like wood or any other filler, we could say, and the roots of mushrooms grow in between the empty spaces and create like a sort of matrix that binds and connects and creates these mycelium composites. For that mycelium to grow, it needs to release some enzymes and break down some nutrients that it finds in these particles. And turns out that as it releases these enzymes, they can like break down super complex polymers that have carbon, because it likes carbon and it likes other ingredients. So as it starts digesting the carbon, guess what? Like plastics are like hydrocarbons. So a lot of people have found that actually fungi can help biodegrade complex polymers. So we decided to use like these two qualities. But first, the second question, can mycelium bind textile waste, and can fibers contribute somehow to the mechanical properties of these mycelium materials? So this was like the second question in our research. And this is what we did, right? The process is called like cascading. So it's like when you take the byproducts of a process and you insert them into the cycle of another process. So we took these fibers that we were using in the starch-based process, and then we just inserted them into the mycelium cycles. In this case, they are called biocycles because it's like living binder that is continuously alive, can be like reactivated. So I'm going to go quickly to this because thank you, Javiera. You did the very nice introduction. So this is mycelium. It's everything that looks white over there. It's the root of fungi. They go in the ground searching for nutrients and creating these amazing roots. This is kind of how you do it. It's a really long process. You have to work in a sterility, but you have to like grow your cultures, think about how are you going to feed these organisms, take out all competitors. That's why you have to work in a sterility. Then you can inoculate your substrate, but it has the amazing property that you can like turn it into like a lot of shapes by molding it, or even by 3D printing it, as like we saw like in the presentation, other speakers like Lucas was showing in their project. So this is how it looks. in the real life, right? Culturing, testing for contaminants, creating the mixture of our substrate. There's Jack's working on it. Then we inoculate our cultures. We let them grow in controlled environmental chambers. And there we have our samples ready for dehydration to stop the living fungi. And then we also perform some testing to understand what was the contribution of those fibers to these composites. So, but before all these things, we also wanted to know, okay, how do we grow this? Like, is mycelium gonna like textile waste, especially like diverse types of fibers? So we did a lot of preliminary experiments to understand what was the format that we needed to put the textile waste. Like, shall we put it just like chopped fibers? Shall we put like the whole fabric? Shall we put like something on top, something on the bottom? How shall we layer or create these materials? So these allow us to understand that we wanted to join two different types of waste streams that were local to create these composites. We not only wanted to use just like textile waste and mycelium, we wanted to bind like these two types of materials or waste streams. So we started working with local waste streams, and in California, pretty similar to Chile, we also produce a lot of nuts. So we started using almond shells and walnut shells as a byproduct of that industry. And those are like the main sources of carbon in our substrate, but we also incorporated other sources of nitrogen. In this case, you can see like some cover crops, fava beans, other cover crops that are used in California, and spent grain from breweries. In California, there are a lot of like craft beer. So we joined these two. I'm going to show this. You can say like, what's that thing? It's like a whole flow chart of how we mix all our ingredients with the textiles, how we condition all the materials and create our baseline substrates, how we hybridize them with the fibers and then sterilize them. And decided to use two strains, oyster and Ganoderma lucidum, Pleurotus austratus, two of the most studied fungal strains towards the creation of mycelium composites. And then we create the sets of samples, and we achieved like these around 59 samples with this condition. So this is kind of like our experiment design. So we decided to test like a baseline that's like without textile waste at 25% fiber volume ratio. So that means like 25% in terms of like volume to the substrate, and then a 50%. We also wanted to understand which agricultural component worked better. So we separated the almonds and the walnuts. So there you can see like the whole range of like samples that we created. So we decided to test for the material properties. I wish I would have more time like during the masters to perform like more chemical, physical, mechanical tests that you perform like during the workshop. So we decided to focus on compressive properties of our materials, and we tested two percentages of deformation, 15% and 30%, compared to the initial height of the sample. So these were like the findings. So what happens if you add textile waste to a mycelium composite? So first conclusion, we find a lot of scatter. That means like the samples, the numbers are like very diverse in each sample. We think this is most likely due to manufacturing. So we still have to solve some issues related to how we homogenize, how we incorporate the fibers to the substrates. We also found that the strength increases after the first compression when there is textile reinforcement. So you perform the 15%, right? And then you, in the same sample, you perform the 30%, and the sample like stands better, like the compressive force. Something else we found is that the integrity of the shapes is like definitely better when they have textile fibers. So samples that did not have textile fibers at a 30%, they would just destroy, rip apart, and yeah, like lose their shape. And if they had textile shape, textile waste, they would like preserve their shape. So that definitely adds something to the material properties, to the mechanical properties. So we published a paper on this. I won't stop too much for speaking about these results. We encourage you later to maybe read more in this paper that we published in the Plate Proceedings conference, very nice conference we attended in Finland this year. And these are like some of the iterations of like some applications or that we did like on these materials. So one of them is like, this is like a sculpture, like, well, let's create a three-dimensional shape using like our substrates and the strains we use. And then this is another one, is like the very early prototype of possible insulation or core for construction, right? Insulation or like furnishings or other types of interior structures or construction structures. So this is cascading, right? We insert the fibers into mycelium biocycles, but what is happening really to the fibers, right? Because I still have this pollutant waste stream made of mixed natural and synthetic fibers, right? So what's happening to them? Are they disappearing? Are they like at the end of their life cycle, they are just gonna end up like in the soils, they're gonna end up in the landfill? Or what's happening? So this led us to the third question of our research, right? So remember the bioremediating qualities of mycelium, right? So can mycelium break down the complex polymers that make up textile fibers, eventually returning them to the soil as nutrients? So bioremediating, right? So to going a little bit deeper, there's been like very interesting research and findings on the this quality of this capability of bioremediating by fungi. There have been some studies performed like on specific types of plastics, polyurethane, an example that comes to my mind at this point, polyester. So we decided to try this. We also had some evidence. For example, this is a very interesting research exploratory artistic project from Officina Corpuscoli in 2011, Mauricio Montalti, which is actually now works with Mogu. So see how this has developed from like a very speculative design practice to something totally functional and commercial right now. So they work here with a specific fungal strain that had been studied and proven to degrade plastic to some extent. We all know these chairs, right? And see how like they create like a layer on top of the chair. They inoculated that layer with the fungi. They let the fungi grow on this layer, and turns out, look at what the fungi did to the chair. So this kind of gives us hope, right? What are we going to do with all these like hard plastics right there? Maybe fungi can really help us deal with this issue. So this part of the research, we called it decaying, which is what is going to be happening eventually in the fibers once they go in each biocycle of the fungal materials, right? Because while the materials are in this like mycelium loop, they can also be recovered. You can grind again like that sculpture that you see there and turn it into the insulation core by inoculating like a 50% more like, let's say, like fresh biomass. So if the fibers are there and the fungi can still like keep degrading and breaking down those fibers, can we eventually get those like fibers to be degraded like on each biocycle? So unfortunately, I ran out of time in the masters. Somehow ran out of also like a little bit of budget. So we couldn't perform this research to the end. We also need new collaborators, especially a lot of knowledge on biology. And I mean, I'm going to talk later about the interdisciplinarity of this team. You're going to see. Yeah, this is our idea on the decaying of fibers. So this is like to kind of wrap up or like synthesize what has been happening. So this is a whole material system, right? Where fibers, or like we have a waste stream that loops, cascades, and then decays. So it's like the thinking how to turn this waste stream into something useful, but also how to really get rid of it. So now that we are in the Biodesign and Industry Week here in Chile, I wanted to bring like a reflection, right, on the like how global problems are local opportunities. And I just wanted to, I was like discovering this amazing thing that happens in between California and Chile, and the textile waste and the agricultural waste that we both have in Chile and in California. So if we draw like a rough line on the equator nearby the tropics, by the way, my country is like right there. And then we locate ourselves, right? See, there's California right there in the corner, and then there's Chile down there in the corner, right? You see that mirror. It's really symmetrical. And I did this exercise this week. Check this. Like if you see from that line, you stand, you look north, see California. And then you look south, see the central region in Chile. See the similarities in terms of like geography. So there are a lot of similarities for real. So this is like an incredible mirror, but there are also some disparities and differences. So for example, think about geography, right? Landscape, weather, altitude, and how that determines the agroeconomy, production, consumption, and export of materials, foods, right? Whatever both countries produce. But think about the society and politics, right? Global North and Global South. And how that, for example, determines the textiles economy, right? How is the production in Chile and in the US, specifically in California? How is the consumption? How are the exports? And also, how is the disposal, right? And how that creates a specific kind of waste availability. And remember, we were saying like waste as a resource, right? So how's the agricultural waste and the textile waste in both countries? Like in California, there's no, at least in the Northern California region, we don't have a lot of manufacturing facilities, so we don't have specific kinds of textile waste, but there's a lot of other types of textile waste that is actually a lot of the times exported to the countries in the Global South. That's why in Chile, we have this problem of the waste in the Atacama Desert, right? And that problem, you also see it in Africa, and you're starting to see it in like countries in Asia, right? So also in terms of the agricultural waste, right? Like, for example, we were testing nut shells in California. So you guys also produce like nuts and like a lot of like very, very similar ingredients, like for creating materials, right? So both places have like abundant ways to remediate, and also biopolymer sources, right? So this is like this represents great opportunity, economical opportunities, innovation opportunities, collaboration opportunities. That's why we are here in UDD, the UCD. So circular materials biodesign. So this is very interesting. So to create circular materials through biodesign, we definitely need design, right? But we also need some craft. We definitely need a lot of science, and we definitely need engineering. We cannot do this just by ourselves, just through one discipline. That's why biodesign, as we have also seen in the talks, especially the ones on Monday, but also through all the work we conducted, like during the week in the workshop, that it's really good to work interdisciplinarily and have all the possible voices, to have like an ethical or sustainable design, to have collaborative design, and also material-driven design, right? Starting from the material, what can we make with it?
Shortly, I want to just bring a very important issue in design. Is like sometimes as designers, we just want to impose the form to the materials. And so we are super astray or like away like from the process of how the materials are made, because we're thinking on the forms we want to create and then imposing them on materials. Materials driven design, or like when designers get more involved with materiality, allows for a different understanding of how materials exist and what can we make with them, knowing that they are like that, right? And they have specific life cycles. So I truly believe that this by design revolution and materials revolution is going to take us to a different understanding of matter and materials and life cycles. So to prove how this is so interdisciplinarily, this is like the team that collaborated in this project, Mycotextile Futures. And on the top, you're going to see the professors that were guiding me during this research: industrial designers, art historian by designer, textile artist and designer, mechanical and aerospace engineer, Akers Lab Valeria. But also we collaborated with a lab in veterinary medicine where we conducted the testing. We used the infrastructure of the Bioinnovation Lab to do all the biological research. We got funding from Zambia National Laboratories. We got funding from the TGIF, which is like more like a sustainability oriented fund in our university. And I also collaborated with these amazing undergraduate interns. Here you have one, Jax, studying design and synthetic biology, but also Mariam Taufik, studying arts and design, Emma Smith, designer, and Alison Rowe, studying environmental design. A bunch of interdisciplinarity, and we still need more people to be involved in this like issue. So definitely thank you so much for like Exploratec and Universidad del Desarrollo for creating this opportunity. Also to my MFA committee, Christina, Beth, and Susan from UC Davis, Professor Valeria Lasaponara from Advanced Composite Research, Engineering and Science Laboratory at UC Davis. So mycelium composite materials are advanced materials, really interesting. TGIF interns, Alison, Emma, Mariam, Jax, funding, the Green Initiative Funds and the national laboratories, and of course, my support with family and friends. And yeah, thank you so much. So open for questions.
Another applause, yes. Questions?
So you talked about using a mixture of, the mixed textiles, right? In order to conduct your study. Was it taken into account the different percentages of mixture materials? Like some clothes have more percentages of synthetic, and others have more percentages of bio materials in the mixture. Was that taken into consideration based on the wide variability you had on the structural testings of the byproduct of mixing it with mycelium and all the process that you just explained?
Yes, thank you for that question. So as you saw, like they were like kind of like 3 questions. So the mycelium part is the question number 2 and question number 3. So in question number 2, we focused on the relationship in between mycelium and fibers, and just like from a mechanical or physical perspective. So we did controlled what were the fibers that we were putting into each sample. So we know what we put into it, and because we work with those 4 pairs of genes, they all had their tags. So it says what's the percentage you have of each fiber. Although I'm just going to disclose this, those regulations are from the 70s. And for example, if the fiber content is less than 3%, they don't have to declare it. I just learned that a few years ago. So even though we have some precision, it's not totally accurate, right? But we control that thing. But for the mechanical tests, like those results, we did not consider them. Because we performed these mechanical tests, but we were not able, due of the time and a lot of other constraints, to perform the more chemical related studies, for example, seeing the material, seeing really that interfacing in between fibers and mycelium, and studying really what was happening in terms of the biodegradation, the biodegradation pathway and the ratio. We couldn't see that. But that is where the compositions of the fibers is really going to be relevant. So that's why we applied to the Futurist Fungi Award, because we want to understand what's happening with those fibers, what is happening at the surface of those polymers, and what are the polymers that are there. Because for sure, it's not just the fiber composition that is stated in the labels, it's also the dyes and many other compounds that have been accumulating during the lifestyle of those clothes, right? So yes. Okay. Oh, yeah.
Ali, I have a question. So since you say that you're gonna you applied for funding to figure out what happens with the fiber, have you guys done any enzymology or whatever is secreted by the mycelium? Let's do it.
Yes. So no, we haven't done that, those kind of research. We would love to do it at the beginning. So we got the TGIF that funded most of this research, along with Sandia. We got it in the last year of my program, which is actually not a year, is kind of 9 months. Oh, yeah, it was actually 5 months. So we reached to the mycologists in our university. There's a department of applied mycology, and there's really interesting people there. But due to the rhythm of the university and many things, we just started the collaboration. And as designers, and we really need to make those collaborations to advance in that part. So we couldn't understand the enzyme, the digestion, what kind of enzymes are being released there, measure any part of that. We we're there. Definitely. Oh, it's attached in the presentation if maybe you're gonna have it. Yeah, she wants our
Hi, something that was just mentioned and that I just started to think about it. Does the use case of different clothing impact the fiber quality at the end of their life? Like if somebody has work jeans and uses them every day for work, gets oil stains, versus somebody who buys a fashion statement and uses them for a month and then throws them away. Is that something that's going to have a big impact on the quality of the waste fibers?
Yes, it is. So during the use phase of the clothes, right? We have different cultural practices for taking care of our clothes, right? We use or not use detergent. We wash our clothes 100 times or 10 times during their lifetime. We work with them or not. Some fabrics have chemical coatings to guarantee specific properties, repellency of water, repellency of stains, or prevention of fire resistance, plus all the chemistry of the detergent, plus all the chemistry of the dyes. The textile industry is so complicated. So that's something we really need to understand, what else is coming there when we are putting this fiber into this material, into this mycelium composites, what other things are we putting there? Because definitely what comes with the clothes really makes something. And just to, we can observe it in our daily lives. When we live in countries with seasons, right? In Chile and in the United States. So when you leave your clothes after the summer and then you take them back the other summer, you see how they smell, right? And they were clean when you put it there, but they have like a lot of remains of other substances, and that is definitely a chemistry that is like acting there. So yes. Any other question? Something in the Zoom?
I have one. Well, I talk a lot about interdiscipline. I'm not sorry about that, actually. It's what I do. So I eat, pray, and love interdiscipline. And by the way, the other day on Wednesday that you mentioned how we are doing interdisciplinary things very well here in Chile. So thanks a lot for that. So there was the chancellor and the deans. So thank you very much. Having international guests tell our bosses that we're doing things great is always good. But well, the question, and I do have a question, and it might be a tricky one, but we need to make the most out of these circumstances. So what's the best about working in such an interdisciplinary way, and what's the worst?
Great. I think the best is that you have the expression of like intellect in all the voices that can participate and perspectives you never knew, like what you are not, the other person might be, right? They can think as you've never thought. How they don't think, you might complement it. And that's really good, like bringing the other voices, the other perspectives, the other understandings. You are always learning something, even though, I don't know, it's a biologist and it makes a weird commentary that apparently is like not related to what you're doing. You're learning because it's like such a different environment than when you develop like in a, for example, my culture is more design, my professional culture is more related to design, right? But I also do a lot of interdisciplinarity, but like in biodesign, you really collaborate with other fields that are like just amazing. So it's learning a lot. And so you have to be pretty flexible on that, which kind of like takes you to the something that is also difficult, which is that you don't have to stick that much to your ideas. You have to be very flexible and be willing to yield your ideas, change your ideas, just let them go sometimes. Do not forget them because maybe they will be useful at other part of the process, but you have to just let that interdisciplinary collaboration happen and let the thing that you're creating become whatever it wants to be, created by the group, right? You if you just try to make your idea using the group, for me, you're not truly collaborating. You're using the group. You have to let all the parts express and let them like, okay, what is it that we are creating? And it's going to take a shape that you're not expecting sometimes. So, and that's a surprise. Sometimes it's really good. Sometimes it's not that good, but that is what it is, right? Something that I consider is really, really challenging is that, how can I say this? Like our corporate cultures and like that includes education. That's super difficult for collaboration because the way that the world like developed, like at some point, it was like different specialties that are all disconnected from each other. And in that same way, like when institutions and when societies grow, they just like create like these old branches and like sometimes very centralized systems, sometimes are like very like isolated systems. So when you want to create something that is like all over the place, jumping from here to there, then you're also going to find a lot of like blocking rules or like logistical stuff. Oh, I need to do this testing on this gelatin. Oh no, this lab is only for woods. Oh, but I need this machine. No. There's a rule. I cannot respond for that. You cannot do it. So you're going to find like a lot of like obstacles that are going to like slow maybe your process. So it doesn't flow as fast as you want. But that is also really interesting because, in nature, things work at their own rhythm. So, and we humans, we always want things to happen fast. And of course, we're going to get in the flow of biodesign and like production of like a more like a sustainable things in a massive way once we start creating better like production systems and adequating the infrastructure that we developed to like the way that now we want to make things. We're gonna get more in the flow, but right now it kind of goes like it doesn't flow that fast. So I think that's like another like a complication that you're gonna face. So it takes more time. It takes sometimes more effort. I'll keep thinking if something else comes out.
I have a question. I'd like to know where you want to take this research. Where are you at in your career, and what are you hoping in terms of doors that might open for you in the next few years?
Great. Thanks for that question. So, well, sincerely, I do this mainly because I'm very curious, and this is just very fascinating. Like, I want to know what's going to happen with all these amounts of trash that we're throwing everywhere. What are we going to do with these microfibers? We should like capture all these materials. They are super toxic, like in all the terms. So I want to know what happens with this. So I really want to keep going in the research, like answering all these questions that I have. And I know it's kind of complicated because that's something for your question, right? If you want to advance like sustainability work, it doesn't advance without the finance or economical like feed. Like it also has to have a feed ground on earth, because like it also needs to be at some point profitable, because that's how we have structured our systems to work. So if it doesn't create any profit, how are you going to run it, right? How are you going to do what you want to do if you don't have a resource, if you don't have no one, if you cannot pay the people that are going to work for you? So that's like a challenge. So I want to connect like these questions of how are we going to solve these material issues with also how are we going to articulate this into something that can really work, and how can we really turn this into a solution where actually we can like take out some of those like super contaminant fibers out of our environments. And right now I know what are the following questions, which is actually that third stage of the research, which is what is happening actually biologically there. And maybe we find that absolutely nothing is happening. That would be kind of sad, but then we can move maybe to another microorganism, right? And maybe I think we're going to find something, because you saw that spoon, you saw that chair, right? There is a chance. And in the winners of the Futurist Fungi Award, like see these two startups working with bioremediation of like super complex hydrocarbon compounds. So I think there's like something promising. So right now I would say like collaborators, people from biological sciences, but also somebody that maybe has the vision of how to make this into like something that connects with the profit, non-profit, like, but ways of like establishing as something that can be scalable. Research right now is like very important, and that could be done through collaboration with industry or with academia. So that will be like probably future steps on this, like for me as a researcher, for us as a team. So yes.
Questions? Alejandra.
Have you been approaching any community on California that could help you, like with the textile waste? And how was your experience with it? Any insight we could use here in Chile? Like we have the same geographical, but not in culture. So any insight we could use to have this to start?
Great question. So this raises a very polemical topic, and I'm going to say something that might be pretty sad for California. But like sometimes, like I think in the United States and in California, there's an understanding that there are no textile waste issues that are so relevant, because it's very difficult to see the textile waste. A lot of the times it is exported to some other countries, so the problem is like thrown away, right? So if I don't see the problem, I don't worry about it. So in terms of like, for example, in the northern region where I am, right, in near San Francisco, Sacramento, like that part, like there's no clothes manufacturing, so there are no scraps, right? The post-consumer waste stream that is more critical is, for example, it's not even like garments, because there are like amazing collection systems in California, although a lot of those garments end up exported to Chile, for example, right? But for if the waste that you see the most is like carpet waste or mattress waste, and luckily and great, this is like amazing in California. They are pretty organized for collecting these waste streams and like diverting it, and sometimes recycling them into or upcycling them into other products that are useful for certain to some extent. So it feels like the problem is like not that much there, or it's like not that present or relevant in terms of communities. But there is one problem that right now is raising a lot of issues in California related to textile waste, which is microfiber release. So right now there are a bunch, or like a couple, I don't know if there are too much or too many organizations and researchers from especially like, I mean, universities like in the, some of them in the coast, a lot of them from the UC system that are trying to understand the problem of microfiber release. I don't know if all you are aware of how annoying and really urgent is like this problem. Like microfibers are like a big constituent of the whole microplastic global issue. Microplastics and microfibers are ubiquitous. They can find everywhere for sure. We have them right now in our bloodstream. We have them in our lungs. We have them in our brain. They're in the food we are eating, and they are contaminating our air and water through laundering processes, through release. For example, we have composite materials that have textile fibers in the tires of vehicles, so they are releasing like those fibers to the air. So there's like now a couple of organizations that are doing a lot of research on microfibers, and there is something super cool called the Microfiber Challenge. And they organized in the past a contest for people creating solutions for this issue. I haven't reached to them yet because I decided to work more with textiles before they are microfibers, but definitely very interested. But I would say in Chile, you actually should have more organizations striving for what to do with these complicated waste streams, because you really suffer from these waste streams in another way. It's like more evident, it impacts your economy, it impacts kind of your daily life as well. Like why in Chile there's not a thriving textile sector. You'll know the neoliberal policies decided to kind of cancel that industry to clothes imports. So you do have like an immediate like effect of that, right? Something also is that the efforts like in the global north are more directed to the preventive. When I showed that slide of the problem and preventive and remediative approaches, so a lot of the biodesign efforts are oriented towards creating new materials that do not create problems, and that is great, right? But in the global south, we're probably not going to have those technologies reach to us as easily as they are reaching in other places. So we really need to start thinking about bioremediating, because nobody else is going to come to the global south and help us with these waste issues. It's our waste now, so we have to find something to do with it, and it's an opportunity too. So yeah.
So I think there's not much more to be said. Certainly there's not much more that I could say to make this any more interesting this whole week. Thanks again, everyone. We had a dream with Christina, growing biodesign collaborations for increased circularity, right? That's the name of the dream, which started a couple of years ago, and now we are able to wrap it up in a place in which people from many different disciplines and many different backgrounds can get together and collaborate for a better future. So there's not much more to be said. Thank you again to all our guests from the University of California, Davis. We have learned a lot from you, and thanks again to our students. It has been intensive, and these are the moments in which you learn the most, right? Thank you for that. So now we have coffee waiting for us outside, and that way we wrap up all this amazing week. Thanks again, everyone, to the Exploratech team. It's been a lot of work. Also to the design and engineering schools, they provided some of the labs and the workshops to work, the textile workshop, the lab downstairs, and so we could conduct all our experiments. So that's it, I guess. We'll see each other at another collaboration.